Chapter 13, Oscillations about Equilibrium, Part 1. So, why do dogs walk faster than humans? Does it have anything to do with the characteristics of their legs? Many kind of motions, such as pendulum, musical vibrations for musical instruments, pistons in the car engines, they repeatedly do the same thing. In other words, they repeat themselves. So we call such behavior periodic motion or oscillations. So what causes the periodic motion? If a body is attached to a spring and it's been displaced from its equilibrium position, then the spring exerts a restoring force on it, which tends to restore the object back to the equilibrium position. This force causes oscillations of the system or periodic motion. The reason that if you push this glider away from the cart, from the air cart, you push this glider away, and this glider is being attached to a spring. But if you do that, the restoring force inside the spring will cause the glider to go back to the equilibrium point. And since this spring has a momentum, so it will not stop. It will go all the way in. So you will have something like this. Okay, it will be compressed, and that will cause another restoring force inside the spring. So this want to push back the glider back to its original position or the equilibrium, but since it has a momentum, it won't stop, so it'll do the oscillation back and forth. Harmonic motion. In the absence of friction, a spring will oscillate around the equilibrium position forever. Okay, so it will do it forever if there is no friction at all, because the friction will turn the energy and change it to heat. So if there is nothing, no friction involved, there's nothing in there to change our energy, then the oscillations will happen forever. This is consistent with Newton's first law. Okay, remember that an object will continue its motion either with a constant velocity or staying at rest until a force applied to it. And then the restoring force of the spring returns it to the equilibrium, which is usually at the point that it does not have any force. But the spring has inertia and momentum, so that's why it's continuing to go past it beyond the equilibrium point and do the oscillations for us. So back and forth motion continues until an outside force stops it, which actually can bring us back to our first point here, which is which can continue if there is no friction forever because of the first law. So this oscillatory motion is sinusoidal. In an ideal spring, and we have seen this before, in an ideal spring, we know that obeys Hooke's law, and Hooke's law is saying that if you stretch a spring, your the restoring force inside that spring is F, and that F is equals to negative K X. X is the amount of the displacement in the spring from the equilibrium position, and it's a vector. So F is a vector, and this K is the spring constant. Okay, it is usually interpreted as how easy or hard it is to compress or stretch a spring. X is a displacement, and as I said it before, and I've said it once, I've said it 100 times before, that this negative sign here, it means that F and X are in a negative direction. If you have a spring and you are applying a force to it and causing the displacement of X towards right, then your restoring force is towards left. That means that they are in the opposite direction. So this negative means whatever direction that you have for X, F would be in the negative side of that. F would be in the opposite side of that. So Hooke's law, the restoring force of the spring, as I said, is F equals negative Kx. And as you can see here, if this is the equilibrium point, is this dashed line, and you are applying a force to this spring and bring the object all the way to this point, so the displacement is X, then the force, which is this bluish arrow here, if you're looking at my cursor, you know what I'm talking about. This force has the opposite direction of this X, and it wants to push the ball or the object back to the equilibrium. Okay, but this has an inertia and this has a momentum, so it will not stop. It will go all the way in, so you'll end up at this point. Okay, now the displacement is towards the left. Your restoring force is in the opposite direction. It wants to bring the object back to its original position, or to equilibrium point, which is this dashed line. Again, it will not stop. It'll go all the way. So you have an oscillations kind of motion here. So characteristics of the periodic motion. The amplitude A of a max is a maximum magnitude of displacement from equilibrium. So this, if we consider this to be the maximum displacement, then this would be our A, okay? This would be the, the maximum magnitude. So the amplitude A is the maximum magnitude of the displacement from the equilibrium. Period T, or capital T, is a time that it takes for the object to do one complete cycle. So going up, coming back down, and going up again. And the frequency is the number of the cycles, or number of these oscillations per unit time, or per second. I mean, I have talked about this in the previous chapters so extensively. So if you don't know what I'm talking about, please go ahead and watch those videos again. So this is per second. Okay, and the angular frequency or angular velocity is omega, and is the 2 pi times the frequency. So omega is delta theta over delta t. Okay, and delta theta, if you do one complete oscillation, going all the way up and coming back down, and then going all the way back to the same point, the total delta theta is 2 pi. And the total time it took it to do this type of motion will be 1 period. But we know that 1 over t, we know this is frequency. So I can show this as 2 pi f, 2 pi times frequency. So omega is 2 pi times frequency. I'll later on show that for a spring, a mass attached to a spring, omega is square root of k over m. So omega is 2 pi f. So 2 pi f is square root of k over m. Okay, in other words, the frequency for a mass being connected to a spring and oscillate, and the frequency is 1 over 2 pi square root of k over m. Okay, that will go inside a box, and period, or t, capital T, is just 1 over frequency, which means that period is 2 pi square root of m over k. Okay, you just have to reverse the frequency that you have over there. So this will be your period for a mass being connected to a spring. Now, there are, as we talked about it, if you start from this point, you go all the way up, coming back all the way down, and going to the same point, you've done one complete oscillation. This is the distance between two maximums or two minimums, okay? This is also wavelength. So if you consider these 2 points, of the 2 maximum points, continuous 2 maximum points, okay? Or 2 minimum points when you see this wave or this type of oscillations. This is called lambda, and it is wavelength, okay? And the amplitude is this much, okay? This amplitude is related to energy or power. So this is amplitude, or this is A, okay? And this is negative A, right? So if you want to know a little bit, maybe go a little bit, deeper on this, consider that you have a circle, okay? And then you have let me draw it so that we have a better idea of what we were talking about exactly. And then you have these two being as your x and your y, okay? And then you have a object with mass m, and this is doing a type of circular motion around this circle. If you imagine that this object has a projection along the y direction, so at this point the projection along y direction is here. At this point the projection along y direction is here. So let me actually draw it. At this point, at this point, this point, this point, okay, and this point. So there is a circular motion happening for this mass m, and then if you consider the projection of the position of this mass m along the y direction, okay, so this is y direction, this is x direction, and then for this point I will have the position to be here. If it's all the way on the top, it will be on itself. For this point, it will be right down here. For this point, it will be right down here. For this one, right down there. And for this one, we're down here. So once it is doing a one complete oscillation or one complete rotation, okay, the projection of this object along the y direction will go up, come back all the way down, and then going to the same spot as it was started. In other words, once it's doing one full circle, the projection along the y direction will go up, come back down, go up again, okay? So it will do something like this. It will go all the way up, okay? And then coming back down, and then going all the way up again, and then coming back down again, okay? Kind of like that. So this is called the amplitude A. This is A, and this is negative A. So I can think of the harmonic motion or these type of oscillations of me looking at a circular motion, but projecting it along the y direction, okay? So I can see that an object is going around a circle, but I am looking at it as if I'm looking at its image along the y direction. Along the y direction, I will have this object going all the way up to the maximum amplitude A, coming back all the way down to the maximum amplitude in negative A, and then going back to its position. It will take it one complete circle to do it. It will take one full period to do it, okay? And if you can, if this object is also moving along x direction, you will see something, a wave-like, something like this. So the object is going all the way up, coming back all the way down, going back up again, coming back down again, kind of like that. Okay, so this would be a concept that I would like you to have it in your mind when you're dealing with this chapter. Okay, so as I said, this is the wavelength, distance between two tops, two maximums, or two minimums, okay? And so, for example, here the wavelength is 1 centimeter, and if you calculate the frequency for this particular oscillation, let's say that it is 30 gigahertz, okay? If you reduce the wavelength, so you have double, if you halve the wavelength, you have double the frequency, because then you will have more oscillations in each unit of time. So you're increasing the number of oscillations, so you're increasing the frequency. So if you have the wavelength, you're going to increase the frequency. If you even reduce it to 1/4, okay, so you're increasing the frequency 4 times, okay, so because you will have more oscillations per second. So a mass on a spring in a simple harmonic motion, okay, so simple harmonic motion is SHM, we'll talk about this in a little bit, has an amplitude A, again, a mass on a spring in a simple harmonic motion. Simple harmonic motion is doing an oscillation like this, going to the left, coming to the right, going to the left, coming to the right. Simple harmonic motion. has an amplitude A and a period t. What is the total distance traveled by the mass after a time travel interval of t? So in other words, if we do one complete oscillation, starting from this point, going all the way back to the same point, I want to see the projection along y direction. So at this point, I have started from here. If this object is going all the way up, I have come all the way up to here, so that's 1a. Now my object is up here. I am coming down here to this point, okay? So I have come down another a. And then from this point all the way to this point, I have come down another a. And then from this point all the way to the same point that I started, I have come up 1a. So that means that I have total distance is 4a for this type of oscillations. So a mass on a spring is, in a simple harmonic motion, has an amplitude A and period t. So we know the amplitude is A and the period is t. Okay. And what is the net displacement of a mass after a time interval t? So we want to know the net displacement, not just the displacement, the net displacement, and how much it actually traveled. Starting from this point, going all the way, going up, down, down, up, coming back to the same point. Did I even move at all? No. So the total net displacement is 0. So let's talk about SHM, or simple harmonic motion. When the restoring force is directly proportional to the displacement from equilibrium. Okay, one more time. When a restoring force in a spring is directly proportional to the displacement from the equilibrium, the resulting motion is called simple harmonic motion, SHM. An idealist spring obeys Hooke's law, and we know what it means. It means that F is equals to negative kx. So the restoring force is F equals negative kx, and that negative means that they're in the opposite directions, which results in a simple harmonic motion. Okay, so simple harmonic motion is a mass being connected to a spring, and it does an oscillations for us, negative A, positive A, without any other force. If the F equals negative kx is the only force being applied to this object. Okay, so I asked you a couple of slides back that this is the image that I would like you to have in your mind. Okay, and we have a little, maybe a better picture here. So I have a mass here that is located right there, and it is doing a circular motion for us. But if I am looking at it from the point of these lights, okay, I only see that this mass is doing this type of motion for me, okay? So it is only going all the way up, coming back all the way down, going all the way up, going kind of like that. And if I can project this along this, piece of paper that's rolling, then I would see these wave type of motions. So if you're looking at this, you will see that there is a wave type of motion here. And x at each point, if you want to find the x for each point, then x is that amplitude A times the cosine of theta, okay? And then I can just write theta as the omega t. Remember what omega was? Delta theta over delta t, okay? So I can write it omega. Delta theta is theta minus theta 0. Omega is theta minus theta 0, t minus t0. Imagine that it was initially starting from 0. It was placed at 0. So then what I would have is omega being theta over t. So then I can write theta being omega t. And then I can use that and place it right there, okay? So instead of theta, I have omega t. Okay, so it looks like this, in other words. If I'm looking at it, I have projected this along one of these diameters or one of these x or y directions. So my position is my object is right here, and it is doing a circular motion for me, going around the circle. Okay, its projection along the x direction. Its projection along the x direction will do the oscillations for me. Okay, so its projections will do. Imagine looking at this. This is what I have done is for y. Projection of this object doing a circular motion along the y direction. Okay, so it will go all the way up, coming back all the way to the same point. But if you're looking at the y direction, the projection of this object along the y direction will do oscillations. Now do the same thing for x. Okay, if you do the same thing for x, the position f, the position x of this object is a cosine theta. Okay, you have a, and this is your theta, so you can find x at all times. So this is a, right? And this is x, the position of the object along the x direction, and this is the theta. A is constant, which is the maximum amplitude, but this theta is changing, right? This theta is changing because your object or the mass that's been connected here is moving, doing a circular type of motion. So if you want to find the x is a cosine theta, and that theta is omega t. Angular speed, as I said, omega is delta theta over delta t. If you do one complete rotation, the time is period, or the time is the time that will take it to do one complete rotation or one cycle. And the change in the theta or angle would be 2 pi. Okay, so, and then we know that we can write it as 2 pi times frequency, or 2 pi f. The object in the circular motion has an angular speed of 2 pi over t, or 2 pi over period. And then this is also not only called angular speed, but also angular frequency. Okay, so it's also called angular frequency. Okay, so what it means is that instead of this omega from the previous slide, I can just substitute this, so 2 pi over t, and I can write 2 pi over t as 2 pi f. Okay, so in other words, I can write x to be equal to a cosine of 2 pi t over capital T. Okay, cosine of 2 pi t over capital T. So I can write it like that. So velocity and acceleration as a function of time. So x is a cosine of omega t. We know that the derivative of x, or x dot, the derivative, if you take a derivative of x, dx over dt, okay, if you take one derivative, then this would be a omega, okay. If you take a derivative of cosine, you will have you'll have a negative sign, okay. So you'll have negative sine of omega t. And then if you take another derivative, this would be velocity. If you take another derivative of x, or x double dot, okay, x double dot, this is only one dot. In other words, if you take two derivatives in a row, dx squared over dt squared, you will have negative a omega squared cosine of omega t, and then this will be your acceleration, okay? Remember, the derivative of cosine is sine with a negative in front of it, and the derivative of sine is just cosine, okay? So these are the two formulas that are important. V is negative a omega sine omega t, and A is negative a omega squared cosine omega t. In other words, this would be the amplitude for the maximum velocity, and this would be the amplitude for maximum acceleration. So this would be V max, and this would be A max. Okay, so a mass on a spring in simple harmonic motion has amplitude A and period t. At what point in the motion is velocity equal to 0 and A acceleration is equal to 0? So if you're looking at this, this is doing this type of oscillations. If this is the equilibrium for me, if this point is equilibrium, okay, equilibrium point, then this will be plus A. We'll do one complete oscillation, we'll come all the way to this point. It'll go all the way to the negative, so this will be negative A, as been indicated here. At this point, it will stop, so velocity is 0. At this point, it will stop as well, so the velocity would be 0. But in that one very second that the velocity is 0, you have the maximum acceleration because it has to come back. And we know that acceleration is change in velocity over change of time. So your velocity has a magnitude before, now it's becoming 0, and then it will have a magnitude again. Okay, so your velocity is kind of like that, is in this direction, then it will stop, will become 0, and then it will be towards the negative direction. So you have a huge amount of change in velocity. In other words, at these 2 points, you have the maximum amount of acceleration. So at this point, I will have A of max and A of max here. Okay. In other words, you cannot find a single point that both have the velocity and acceleration being 0 at the same time. You either have one of them being maximum and the other one being 0. For example, at the center, okay, at the center, the velocity is maximum. So at this point, the velocity is max, but there is no acceleration. The acceleration is 0. The velocity is not changing that much, so the acceleration is 0. Okay, but over these points, over these 2 points, the amplitude, the maximum and minimum amplitude, you have 0 velocity because the object will stop, but then it will quickly go back, so you have a huge amount of change in velocity. So you have the maximum acceleration. So I told you that I will prove how we found that the omega is square root of k over m, okay, right here. So let's take a look. X is a cosine omega t, and a of x, or the acceleration, is negative a omega squared cosine omega t. If you put them in Newton's second law, or F equals negative kx in our case, okay, if you put it there, then and we know that F is also ma, okay, so negative kx equals ma. So negative kx, and x is a here, okay, and a is what I have right there. Then what I would have is that negative kx equals ma. So negative k, x is a cosine omega t, okay, equals m. A is negative a omega squared cosine omega t. Then you can get rid of cosine omega t from both sides. You can get rid of a from both sides. You can get rid of negatives from both sides. You are left with k, which is being equal to m omega squared, and omega would be k over m under the square root. Okay, so that's how you prove it. And you know, in order to find t, then you will have 2 pi of m over k. I proved it in the beginning of the video. So these are the very 2 important formulas. If you have one, you can find the other easily. So a glider with a spring attached to each other and oscillate with a certain period. If the mass of a glider is double, what will happen to the period? So let's write down things that we know. So a glider with a spring attached to each and oscillate with a certain period. So we have a constant value for t. If the mass of the glider is double, m becomes 2m. Okay. What will happen to the period? So we'd like to know that what would happen to this period. We know what the t is. So I have 2 pi square root of m over k. Okay, as I have it right here, t is 2 pi square root of m over k. All right. So if you double the mass, what you're doing is this. You have t 2 pi square root of m over k times the square root of 2. Okay. Because you know in math that if you have a square root of a times the square root of b, you'll have a square root of ab. Okay, so they both will be under the square root, or you can separate them. And I did the same thing here. All right, so in other words, the new t will be the square root of 2 over the old t times the old t. So in other words, and this, since this is square root of 2 is about 1.4, so you have increased it. So the period will increase. So in other words, the t new will be longer than t old. Energy. A compressed or a stretched spring exerts a restoring force to return to the equilibrium position. We know that. Force moves an object attached to the spring, and the spring will do some work for us. We know that as well. So we know what the work is. Work is in terms of energy. It is half kx squared. We know it from previous chapters. Please go ahead and watch the videos if you forget, or at least go over it in the book. A compressed or a stretched spring held in a position will restore the energy, because as soon as you release it, imagine that you have a spring, okay, and you are holding it with your hand. Okay, as soon as you let this spring to leave your hand, it will go back to its original position, or equilibrium. So there is a force involved when you're holding it. So there is some sort of a potential energy is being released, because once you release it, once you let the spring go, it will go to its equilibrium position. Okay, so there should be some sort of a potential energy stored inside the spring. So we know that elastic potential energy, we've talked about it before, is half kx squared. The elastic potential energy is the energy that a spring has by virtue of being stretched or compressed. Okay, and how did we find this? We used the work energy theorem to find it. For an ideal spring, the elastic potential energy is half kx squared. We've seen this before. If you remember, in order to find omega, or in order to find W, the work done, we would have to do this. Okay, and then we had negative kx dot dx, and then this negative and negative will cancel out. So you'll have a positive k, the integral of x dot dx, and then you'll have a positive k. X dot dx will give you half x squared. So in other words, the work done is half kx squared, and we know that the work is in terms of energy. So the potential energy stored is the amount of work that the spring does, which is half kx squared. So energy in simple harmonic motion, and mass oscillates in a simple harmonic motion. So it's attached to a spring then with an amplitude a. If the mass is doubled, but the amplitude is not changed, so I have changed my mass to 2m, so from m to 2m, but the amplitude does not change, what will happen to the total energy of the system? Let's talk about, but A has not changed yet. So A is the same. So let's talk about the energy. Energy, kinetic energy is half mv squared. Okay. Potential energy is half kx squared. Okay. Now, if you're looking at this, U at the maximum point is half k, the maximum point, x will be amplitude, so I have a squared because x of max, the maximum amount of displacement along the x direction is just the amplitude if it does the oscillations, okay, going all the way to positive a and to negative a. So if that's the case, the u maximum will be half kx a squared, all right? In other words, and at that point, there is no velocity, okay? So there is the k kinetic energy is zero because there is no velocity involved, okay? So this is at max point, okay? So this means that since A is the same, K is a spring constant, it's the same, the total energy is conserved. However, the kinetic energy is half mv squared. Okay, if m is doubled, then what you need to do is to change the energy, the velocity, to this. This will happen because you want to have the same amount of energy, because at the point max, you have the same amount of energy. So the total energy will not change in our case. So let's talk about this. We've talked about it before. If you have a mass oscillating back and forth, so if you have this, for example, and you have a box being attached, so this is M, and then you have this oscillations, it's coming all the way to this point, okay, point A, and it'll go all the way to this point, to point negative A, okay? What is happening is this. At this point, if all the energy is potential, U, and your kinetic energy is zero because it will stop. So U is half Ka squared. At this point, all the energy is again potential. Kinetic energy is zero because their object has stopped. And the potential energy that you were talking about is half Ka squared. At this point, the potential is zero because x is zero, but velocity is maximum velocity. So you have k being the maximum amount of possible, the maximum amount of kinetic energy. And then k max is just half mv max squared. Okay. So when it comes to the work, we know that the work of elastic forces, or forces like a spring, is just a change in the potential gravitational is just a change in the potential energy. And if you write down the mechanical energy is the total amount of kinetic energy plus total amount of potential energy. Okay, so this could be the kinetic energy of transition plus the kinetic energy of rotation, which you have it right there. Half mv squared is transition from one point to the other, and then half I omega squared is the oscillations or rotation. And then the total potential energy could be the potential energy of gravity, which is mgh, plus the potential energy from spring or elastic forces, which is half kx squared. So, and there are situations that we have all of them. Okay, so this is k and this is U. So we'll talk about pendulum in part 2 of the video. This is the end of part 1. If you have any questions, let me know. Otherwise, go directly to part 2 of this video in chapter 13 and watch it right now. All right, we'll continue next with part 2 of chapter 13.